Hello everyone. In today's lecture we will introduce the concept of complex power. So up to this point we are familiar with the concepts of real power or average power. So average power is what we call real power. And then there's although it has units of watts, right? So this is the typical unit of power, VA, right? This is the unit of power, VA. Right? And then we introduce the concept of apparent power, which also has units of VA, but we don't call it watt. To distinguish it from real power, we just designate it with units VA. So if we're talking about real power, we say 5 watts. If we're talking about apparent power, we say 5 VAs or 5 VA. Okay. So we're going to introduce the concept of complex power that kind of ties those two ways of looking at power together and adds a third component, which is called reactive power. Okay. Typically, let's introduce that. Let's go back to our power formula. So the average power formula or the real power formula that we've established is what is VRMS. I'm gonna write it using the RMS values. IRMS cosine theta V minus theta I. Okay. We can write this in an alternate form. We can, right? So this looks like what? So if I can write it this way. I can write it as some magnitude, VRMS being the magnitude of some phasor, right? With theta V, right? I want to get the minus sign here. So what do? I multiply by IRMS and then put an angle of minus theta I. This allows me to get the negative sign here, right? Now this is a complex number, right? So I need to take its real part to get what I'm gonna get, to get the expression above, right? So I mean, look at this. Examine this. This is exactly the same thing as what I've written above, right? This is just a reformulation of what I've written above. Take this expression, which is just VRMS, IRMS, theta V minus theta I, right? This is a complex number, and take its real part. Its real part is just, the magnitude times cosine the angle. So if I have a complex number, and this is the angle of the complex number, and this is the magnitude, right? Then the real part is just m cosine theta, right? It's just a projection on the real axis. So I didn't do anything. I just rewrote this expression in this way. Okay. Now this complex number inside those brackets, that if I take the real component of, I get average or real power, this is called complex power. And it's a very useful expression or quantity. It makes calculating power in AC circuits simpler. But let's examine more carefully what it is. So this is called complex power, and it's designated by S, right? And what this is, right? So this is a phasor. What this is, and sorry, S is not a phasor. S is a complex power. It's like impedance. Impedance is a complex quantity, but not a phasor. S2 is a complex quantity, but not a phasor. But it's constructed from multiplying together two phasors. What kind of two phasors? Well, this first one is the VRMS phasor, right? So it's a phasor that has its magnitude equal to the RMS value of the AC voltage waveform, and its angle is the angle of the voltage, right? What does this look like? Is this IRMS phasor? Well, almost. Notice that there's a negative sign that we needed to add here to get the right expression for the complex power, for the real power, right? What happens if you take a complex number and you make the theta negative? So this is minus theta. you get the complex conjugate, right? So making the angle negative is an act of conjugation, right? So this is IRMS phasor conjugate. This is the general expression for complex power. And it's a very useful complex quantity. You calculate it for any element or any part of a circuit, and you take its, if you want to get the real power out of it, you just take the real part of it, right? What if you wanted to get the apparent power? Well, clearly the apparent power is just the magnitude. Right? So clearly magnitude S is just VRMS IRMS, so magnitude S is clearly the apparent power. And what's its angle? So what is angle S? Angle S is clearly theta V minus theta I, which is, right, and the minus again comes from the act of conjugation. This is clearly the power factor angle. So the complex power is a complex number whose magnitude is the apparent power. Its angle is the power factor angle, and if you take its real part, you get the real or average power. Okay, so S is a complex number. We can rewrite it as follows: P plus J Q. Right? We know what P is. It's the real power. This is new now. This imaginary part of the complex power is, we haven't talked about that yet, but we will introduce it now. Right? So and what's P? We will introduce it now. But what's P? P is, in this case, just evaluate this, right? It's VRMS IRMS. That's the magnitude of S. I'm just multiplying the magnitudes of those phasors, right? And then cosine the angle, cosine theta V minus theta I, and again the minus comes from the conjugation, plus J, right? So this is P. Now let's do the complex part. The complex part is just the projection on the imaginary axis, which is the magnitude times sine theta, right? So in this case, it's going to be VRMS IRMS sine theta V minus theta I. Okay. Now this part is Q, right? So Q, we said, is called the reactive power. Okay. So it's another kind of power which we call the reactive power. We will discuss its significance and why do we need to calculate it in a bit. But let's talk about units a bit. Okay. So we said S is complex power. Right. The magnitude of S, if you take its magnitude, that's the apparent power. That's what amount of power the circuit or the element is processing apparently, right? And that we said to differentiate it from any other kind of power, although the units of power, any kind of power, are going to be always watts or V times A, voltage times amps. We want to differentiate the different kinds of power. So there's a convention of calling apparent power VA. So we say 20 VAs or 30 VAs. P, which is the average power, is just the real part, or real power is just the real part of S, real or average power, right? So this is real power or average, right? And the convention is to use the classical watts for this power, because this is, in many ways, this is the actual energy that's being dissipated from the element. This is what causes heat in the element, right? This is what you extract from the power system. Right? Reactive power is just the imaginary part of S. And briefly, Q represents the amount of power that is kind of like sloshing around in the system. Right? We said, for example, a capacitor and an inductor don't consume or absorb any average power, but they continuously sink in and give back power. So there's continuously some power sloshing around in the system, and the measure of that power that's sloshing around and oscillating in place in the system is called reactive power. So this is called reactive, or quadrature. Right? And to distinguish reactive power from apparent power and real power, we designate it has units of V times A, but we designate it as the unit we use for it is called var. So we say, hey, in this inductor or this capacitor, there's like 50 vars being absorbed or consumed, right? Var stands for volt ampere reactive. Okay. So those are like the three different kinds of power that we get all bundled together into the single concept of complex power. So the concept of complex power gives us those three different ways of looking at power. Okay. A good analogy to differentiate between a real power and imaginary power or reactive power is as following. Imagine a river that is flowing, right? And imagine the water in the river is energy, right? So real power is really the tendency of the water to move downstream in one direction, right? It's how much volume. So if you took the cross section of the river, how much volume of water is flowing in time, right? Let's say 50 million gallons per minute or something, right? There's constantly some amount flowing, right? So that's a measure of like P. That's analogous to P. Reactive power is you could have superimposed on this flow some wave action, meaning although there is some flow on average, there is some flow like in this cross section, there is some flow that is wavy like this. Like you have water that's passing the threshold, but then it's coming back. So it's constantly moving back and forth. So the water is constantly passing and then coming back, passing and coming back in a wavy fashion, right? No actual displacement of water is happening. The water is not moving downstream, it's staying in place, it's only moving back and forth. That's still an activity, right? There's still energy there, but it's not energy that's moving forward. It's energy that's sitting in place, right? And it's just displacement in place. So this kind of thing is analogous, this kind of movement is analogous to Q or reactive power. Of course, apparent power is just the magnitude of both, without regardless of what is moving downstream and what is sloshing in place. Okay. So this is conceptually how you understand those different kinds of power. Okay. So let's tie this this complex power concept to all the basic circuit elements that we know, right? So let's start with the resistor, and let's apply the sign convention for voltage and current. Remember, so the sign convention is if the voltage is positive, right, the current flows this way. This is the sign convention that allows us to calculate absorbed power in the element. Because if we use this convention and whatever power we calculate turns out to be positive, that tells us that this power is being absorbed in the element. If whatever power we're calculating turns out to be negative, using from this convention, this tells us that this power is being supplied by the element. I would expect a resistor, and we're using this convention, to only absorb power. Right? Of course, if you change the convention, you're allowed to change the convention. It's just a matter. That's why it's called a convention. If you make the sign of the current this way, right, then a positive value for power means that's power that's supplied by the element. A negative value for power, that means it's power that's being consumed or absorbed by the element. Of course, because this is a resistor, I should expect my power calculation here to turn negative, to be negative, because the resistor naturally cannot supply power unless it's a negative resistor, which doesn't exist. It's not real. You have to build a circuit to kind of emulate a negative resistor. So we know this fact: resistors only absorb real power. Okay? So what's P? Well, let's do S first. S is V RMS, I RMS conjugate, right? So this is, phasors. So this is V RMS, theta V, I RMS, theta I. Because it's conjugate, I put a minus sign. And I end up with P. The real part of S is the real power, which is V RMS, I RMS cosine theta V minus theta I, right? And for a resistor, this is 0, right? Theta V equals theta I, so this is 1. So it equals V RMS, I RMS. This is larger than 0 using this convention, the signs. Okay, so the real power is larger than 0. Q, right? For resistor, Q should turn out 0. There is no quadrature or reactive power in a resistor. Power always flows uniformly. And we can verify that. I can take now the imaginary part of S, which is V RMS, I RMS, sine 0, which is 0. Okay, so we've shown that a resistor has only real power flowing through it, and all the apparent power is equal to the real power. All the apparent power manifests as real power. Okay, so only real power flows through it, and no reactive power is flowing through it. Okay. Let's take an inductor. So this is L, this is V RMS, I RMS, right? And we know for an inductor, the current is always lagging the voltage by 90 degrees. I mean, why is that? I mean, we know that V RMS equals the impedance, which is J omega L I RMS. So the angle of the voltage is always the angle of the current plus 90 degrees. J is 90 degrees, right? So the current for an inductor is always lagging by 90 degrees. Let's use this fact. Let's calculate P. P is V RMS. Well, let's do S just for completeness. So this is V RMS, theta V, I RMS minus theta I, right? But we said for inductors, the current is always lagging the voltage by 90 degrees. So theta I should be theta V minus 90 degrees, right? It's always behind the voltage by 90 degrees. So this equals V RMS, I RMS, theta V minus theta V plus 90. So this becomes 90 degrees, right? So P is just V RMS, I RMS, cosine 90 degrees. Aha, what's cosine 90 degrees? 0, right? So that verifies what we knew already, that the inductor does not absorb any real power. What about the reactive power on an inductor? So the reactive power is going to be V RMS, I RMS, sine 90 degrees. What's sine 90 degrees? 1, right? So this is going to be V RMS, I RMS, larger than 0. So the inductor, in this case, in the case of the inductor, the apparent power, which is V RMS, I RMS, we can say that all of the apparent power manifests as reactive power, and nothing manifests as real power. It's like you're taking the apparent power and you're distributing it as either a real power or reactive power. So in the case of an inductor, P is 0. There is no power absorbed, but there is positive reactive power absorbed. This amount of energy that keeps sloshing in the system. Right? So we say that an inductor, this is a fact, absorbs reactive power. Of course, this is based on our convention for V and I. and we said the units for reactive power is vars. So we say that, hey, this certain inductor is absorbing 50 vars or whatever. Okay. Final element is the capacitor. So let's take a capacitor. You apply VRMS, IRMS phasors. For the capacitor now, the current leads by 90 degrees. And we can show that from Ohm's law, right? So VRMS equals 1 over J omega C IRMS. That's the impedance for the cap. We established that, right? And we have 1 over J, which is an angle of minus 90. Right, so the voltage is at is the same angle as the current minus 90 degrees. Okay, so we can write S for this. S is going to be VRMS IRMS conjugate, VRMS, let's say theta V, and then we say IRMS theta I. But we know that the current is leading, right? So the angle of the current is going to be theta V plus 90 degrees. Oh, I made a mistake here. So this is minus theta I because it's complex conjugate, right? So I put in, instead of minus theta I is theta V plus 90 degrees, right? So it's going to be minus theta V minus 90 degrees. So I end up with S being VRMS IRMS theta V minus theta V and then minus 90 degrees. Now we have minus 90 degrees. So now P is still the same. P is VRMS IRMS cosine minus 90, which is still 0. It doesn't matter. The cosine is an even function, right? But now Q is VRMS IRMS sine minus 90 degrees. The sine is an odd function. Sine minus 90 degrees is minus. So it's going to be minus VRMS IRMS. So we established the fact that using this sign convention, and you always use this sign convention for power, right? The capacitor supplies reactive power because the sign turned out to be negative. So this is less than 0. So we say a capacitor supplies reactive power. Right, so that's interesting. It does the opposite of an inductor. The inductor absorbs reactive power, meaning using that convention, and then the capacitor supplies reactive power. The way you can see this, if you look at the energy, so we said that reactive power is kind of like energy sloshing in and out of a system, right? So we said the real power is kind of like constant flow of energy. Reactive power is kind of like energy sloshing. So energy is going maximum, going low, going maximum, going low. There's no energy continuously being absorbed. Energy is sometimes absorbed, goes positive, or sometimes absorbed. The positive is absorbed using this convention, sometimes supplied. So energy is moving back and forth. Right? What do we mean when we say that the using this convention? What do we mean when we say that the inductor supplies energy? Absorbs the reactive power, and the capacitor supplies reactive power. Well, it means simply, this is E. If I look at the energy flowing in and out of an inductor, let's say, so it might look like this. So this is energy sloshing around. Sometimes energy goes positive, sometimes it goes negative. I mean, I'm approximating it. It might not look exactly like this. I don't know what the frequency is. I don't want to calculate that. It definitely won't be the frequency of the line, by the way. It won't be 60 hertz. It will be like double it, 120 hertz. Right? But I don't want to go into that right now. So this is inductor. If you look at the energy being sloshing around in the capacitor, it will be opposite. It will have this opposite orientation. That's why the signs of Q, that's why for an inductor Q is positive, here Q is negative. So kind of like energy sloshes around in both, but they sloshes around in a negative orientation with respect to each other. Okay. And we can say, I mean, intuitively that the reactive power Q, ultimately, the amount of energy sloshing around relates to the energy stored in L and C. Okay. What about the complex power for a general impedance? Let's say we don't have a pure R or L or C. We have a combination of R, L, and C. So I have ZL, some load, then I have VRMS, and then I have IRMS here. Okay, so what's S in this case? S is VRMS, IRMS conjugate, right? So how do I evaluate that? What's happening here? I mean, let's recall Ohm's law. Well, that's all we need, right? Whenever you see an impedance, you think Ohm's law. Right? And let's plug that in. Let's start with IRMS. Let's plug in, instead of VRMS, IRMS. So in this case, S becomes IRMS Z times IRMS conjugate. What happens when you take a complex number and multiply it by the conjugate? You get the magnitude squared, right? That's a basic property of complex numbers. Complex number times its conjugate. Let me write this another way. Let me call the complex number V. V times, no, complex number K times its conjugate equals magnitude K squared, right? So the magnitude of the phasor IRMS is just IRMS. So this becomes IRMS squared times Z. That's a basic property of multiplying a complex number by its conjugate. Right, so that's what S is. So S in this case is IRMS squared. Z is just R plus JX. This is equal to P plus JQ. So we can say P is just IRMS squared R, and then Q is just IRMS squared X. Right? So this, you can see this comparison clearly, right? P is just IR. So when you have a situation where you have an impedance, if you want to find the real power, just take the IRMS value, square it, multiply it by R. If you want to find the reactive power, just take the IRMS value, square it, multiply it by X. That's it. Okay. Of course, we can apply Ohm's law differently. We could substitute IRMS. IRMS is VRMS over Z, right? So I could say this. So I could rewrite Ohm's law as follows. I'm allowed to do that, right? So it shouldn't matter. So this equals VS VRMS phasor over Z conjugate. This allows me to write S in terms of admittance, because admittance is the inverse of impedance, right? So this becomes VRMS phasor conjugate. 1 over Z is Y, so this is Y admittance. You know that if you have two complex numbers, Z1, Z2 conjugate, this equals Z1 conjugate, Z2 conjugate. That's a basic property. Okay, you can check that. I mean, make sure you see this. But this is a very basic property of conjugation. You can always distribute conjugation over either addition or multiplication. So this equals VRMS squared. What is admittance? We said admittance is just conductance. I want to separate it into the real and imaginary part. It's just conductance plus susceptance. The imaginary part is called susceptance now, but now we have a conjugate here. So this equals P plus JQ. Okay. Aha. So now we are faced with a situation where we represent the impedance or the circuit complex circuit that have multiple elements in it by an admittance. In this case, we say P. In this case, if we represent the circuit by or part of the circuit by an admittance, the easiest way to calculate P and Q is to find the voltage across that admittance, that whole circuit, and then P is just V RMS squared G, right? What is Q in this case? Q is V RMS squared B, but that's not correct. There should be a minus sign. Why? Because this is conjugated. So this is actually G minus JP. Right? So Q is going to be minus V RMS squared times the susceptance. Right? So those two formulas can sometimes be useful when you reduce the impedance of a whole section of a circuit or a whole circuit into just an impedance, one single impedance block or one single admittance block. Okay, and even if you forget those, if you have seen, those are very easy to rederive. Okay, so for example, for an inductor, so what's the impedance of the inductor? So we said it's IRMS squared Z, right? What's the impedance of the inductor? Impedance of the inductor is just J omega L IRMS squared. Right? So this confirms that for an inductor, Q inductor is just the real part of the imaginary part. We take the J out, is just omega L IRMS squared. That's the reactive power. Okay, for a capacitor, I could take the admittance of the capacitor. In this case, I have to take VRMS squared times the admittance of the capacitor. So I use the conjugate of the admittance. Right? So I use this formula, VRMS squared times the conjugate of the admittance. I'm using this. What's the conjugate of what's the admittance of a capacitor? If the impedance of the capacitor is 1 over J omega C, the admittance is J omega C. The conjugate of the admittance then is going to be minus J omega C. So this equals minus J omega C V RMS squared. So that tells me for a capacitance, Q is minus omega C V RMS squared. Okay. You have to be comfortable with all those manipulations. So I guess this comes with practice. We haven't done homeworks yet on this section. I guess once we're done with it, I'm going to give you like a homework to practice on those things. Yeah, I'm sorry, I've been a little like last week where we had the midterm, and then it was kind of like a hectic week for me. So although as far as the material is concerned, we're not behind per se, because some of the material went faster than I expected, but we're still like a couple of lectures behind. So I try to, but we have some days off with no lectures too. So I think we will catch up eventually by the end of the semester. Okay. So let me present this in another way. I want to give a graphical interpretation of complex power and power in general. Okay, so we said we have V RMS, let's say. I'm representing the phasor, the RMS value of the phasor. Right, and the current is at any angle. So this is not purely inductive or capacitive or resistive. This is some random combination, right? So the current can be at any angle. So the current is an angle theta I, the voltage is an angle theta V, and then this thing here, this angle here is theta V minus theta I, right? What we could do is we could project. Let me change the color of the pen. We could project this current into a component that's in the direction of the voltage. That component will have a magnitude I RMS cosine theta V minus theta I, right? And then I can project it. I'm decomposing it. I'm decomposing the current into two components. It's just exactly like vector decomposition, only it's happening with complex numbers. So I can, this component is going to be, and that's the nice thing about phasors, by the way. They behave identically to vectors. Any vector manipulation that you know, or except the scalar product, which doesn't mean make sense for phasors, or the scale or the cross product, but any other vector addition and summation and subtraction and scaling you can do with phasors. They are identical to vectors in every respect. Okay, so this projection has a magnitude of I RMS sine theta V minus theta I. So using this graphical interpretation, it's clear that if you take the current phasor and you project it on V, so this is called, by the way, the direct component. So this projection of I phasor on V is called the direct component of I. It's clear that if you multiply the magnitude of V with this direct component, you get P, right? So this is what P is. If you take the magnitude of V and you multiply it with this component, which is called the quadrature component, you get Q. That's also another source or a reason for choosing Q. Q stands for quadrature. Okay. Right. So that's like a useful way of thinking about it. Hey, you have the voltage phasor and you have the current phasor, right? Just decompose the current phasor into two components, into a component that's in the same direction as the voltage. This is called the direct component, D, and into a component that is 90 degrees from the phasor. This is called the quadrature component, Q. I'll use Q small for quadrature. Okay, and this allows you to easily calculate P and Q, right? And to see that, so this is a very common geometrical interpretation for our method for finding P and Q. Just taking the current and decomposing it into direct and quadrature components. And this is clear. I mean, we can see that. So we say that S equals V RMS I RMS D. This is clear. I mean, it's clear how this part. Let's show that the direct component gives us the real part, the real power, and the quadrature component gives us purely the reactive power. Let's prove that actually to ourselves. So I said I took the current, I decomposed it into a real and quadrature component. So let's take S for that part. So this S equals V RMS and then I RMS conjugate, right? V, this is equals to V RMS theta V. This is I RMS minus theta I, right? I RMS, sorry, this is direct. So I'm only interested in finding S for the direct component, right? But what's the property of the direct component? The angle of I RMS D is equal to V RMS. So the angle here, so this is going to be V RMS theta V I RMS direct. Remember, this is just the direct component minus theta V. Theta V minus theta V is 0. So you end up with S being just real. It's going to be V RMS I RMS D. What about S for this component now? For this component and the voltage. So that's going to be V RMS I RMS, the quadrature component, conjugate. So this is going to be V RMS theta V I RMS Q minus theta minus the angle of the quadrature component, right? Because it's conjugate. But what's the angle of the quadrature component? Is the same as the angle of the voltage, minus 90 degrees, right? In this case, because the decomposition is like that, the angle is minus 90 clearly. Right, so this is going to be minus 90 degrees. By the way, it's not always minus 90 degrees. Sometimes it's plus 90. So if I have the voltage here and the current is here, the decomposition becomes like this, right? And the angle becomes plus 90. It doesn't always, it depends on where the current phasor is. Right? But in this example, it turns out to be minus 90 degrees. Right? No, it's not minus 90 degrees. It's minus theta V minus 90 degrees. Right? That's the angle of I. So we end up with theta V minus theta V plus 90. So we end up with V RMS, I RMS, quadrature component of I RMS, 90 degrees. 90 degrees is just, 190 degrees is just J. So this is Q. This gives me purely Q. Okay, so this shows why decomposing the current into a direct quadrature component is a valid way of arriving at the reactive real power and the reactive power. Okay. Going back to the formulas, so we said what? S, let's do P and Q. P equals, yeah, so one basic relationship I want to give you, which is apparent really, but I just want to write it down, which is this equals V RMS, I RMS, cosine theta V minus theta I, Q equals V RMS, I RMS, sine theta V minus theta I. What happens if I divide those two equations together? I end up with sine over cosine, which is tan. So tan theta V, the tan of the power factor angle equals Q over P, right? I mean, this gives me something called the power triangle. So the tan of theta V minus theta I is just QP, right? And what's the hypotenuse? What's P squared plus Q squared? Well, it's the apparent power, right? Because if I take this thing, square it, and then take this thing, square it, I end up with cosine squared plus sine squared, which becomes 1, right? If I take this out, I end up with V RMS, I RMS squared, which is the apparent power squared. So the apparent power squared equals P squared plus Q squared. Solidifying that there is a sort of triangle there is a power triangle. I mean, this is very basic. You can derive it from the expressions for S and P and Q, but this will always hold. The apparent power is the magnitude of S. The apparent power squared will always equal P squared plus Q squared, and then the angle between Q and P, the angle of this triangle is going to depend on the power factor angle, the angle between V and I. This brings us to another way to view. I mean, we can view complex power as something that exists in the complex plane, and this introduces the concept of the power quadrants. So sometimes when you kind of like buy a power supply for the lab or something, or for some specialized power supply, sometimes they say, hey, this is a single quadrant operation. This is a 4-quadrant power supply. What does that expression mean? What does it mean when people say this is a 4-quadrant power supply? That refers back to complex power, right? Because we said S equals P plus JQ, right? When we say it's a 4-quadrant supply, that means it's a supply that can generate S at all 4 quadrants, meaning we can have a situation where we have real power, positive real power, the supply is generating power, supplying power, and then positive reactive power. The supply is supplying reactive power. We could live in this quadrant. The supply could supply positive real power and then absorb reactive power. The supply could live in this quadrant. it could absorb real power. So the supply could act like a charging battery. Batteries are being charged. It could absorb power from outside itself, absorb real power or average power, and supply reactive power, or it could absorb both sorry yeah, this is when P is negative, it's absorbing. So it could also absorb real power and reactive power, so it could live in this quadrant. So that's what it means when you hear the phrase the supply, and you might hear that if you want to buy supply, whatever capacity you're in, right? You might hear people talk of four quadrant supply. That's what it means. It's talking about yeah, the power capability of the supply. It can absorb or supply real and reactive power. It could live at any point in this quadrant. If it's a supply that can only generate power and it cannot sink power, it will live in this quadrant, in those two quadrants. P will always be positive and Q could be positive or negative. Okay. The final thing I want to state is I'm going to go back to what's called Tilligan's theorem, which is a simple theorem. It states, and it follows from the conservation of energy. It follows that in any circuit, however complex the circuit is, at any point in time, the total energy supplied for any element is zero. Meaning if you calculate the total energy supplied by this element or this element, sum them all up, the sum should be zero. Meaning at any one moment, the total power supplied equals the total power absorbed, and the total power absorbed equals the total power supplied. There is no energy being created out of a vacuum. Any energy that is absorbed somewhere in the circuit is being supplied from somewhere else. And this also applies to S. The sum of S supplied in a circuit is zero in an AC circuit. All the absorbed complex power in the circuit equals all the supplied complex power in the circuit. Right? And this also comes from the concept of conservation of energy. Let's do a bit of examples. The example is as follows. Right, so you are told that there's a certain load, factory or whatever, right? So this certain load is at a level of 20 kilowatts, but that's not enough information. I have to give you the power factor. So it has 0.8 power factor, but that's still not enough information. I have to tell you whether the load is leading or lagging. So this is lagging, meaning the current is lagging the voltage by certain amount. Okay. Then furthermore, I tell you that the voltage at the load is 220, 0 degrees. The voltage at the load is the reference, right? And this is at 60 hertz, right? And then the utility supplying power to this load has a transmission line. So the impedance of the transmission line is given at 0.09. But there's a twist here. I mean, previously in the previous example, we only gave a transmission line, example of transmission line that's purely resistive. Transmission lines actually have also intuitively a reactive component, an inductive component. All long wires have an inductance, right? So this is now a more realistic model of the transmission line. It has an impedance of 0.09 resistive, and then it has a reactive component, inductive component, 0.3 ohms. So the question is, what is the voltage and power factor at input of line? If I draw it as a circuit, it will look like this. This is the source coming from the utility, the generator, and then this is the transmission line, 0.09, and then the inductive part, reactive part, J 0.3, and then this is the load. So this is IL, represent the load as a box, and then this is 20 kilowatt, that's what's consumed, the average power, real power, and then 0.8 power factor lagging. And the voltage on the load is measured to be 220, and it's a reference, phasor reference. We set it as angle 0. Okay. Now we want to solve for the voltage at the source, this voltage, and the power factor of this complete circuit, not just the load. Okay. Now we could, I mean, there are many ways again to solve this. We could, just deduce what V and I is for this load, and then use like KVL technique. It's just a circuit, and you can solve a circuit in multiple ways. But we want to utilize the power, apparent power, reactive power, real power, and complex power concepts that we've learned to solve this problem. We don't want to go back to KVL. We want to use the new concept that we've learned. Okay. So the first thing we can do is what? So we know the real power and we know the power factor. What is the apparent power? So this is it. What is apparent power? Apparent power is the complex power at the load, its magnitude, right? That's what the apparent power. But we already know what the apparent power is. Apparent power is just VRMS, IRMS, which is P. Sorry, the apparent power is P. What is P? VRMS, IRMS, cosine theta V minus theta L, right? So P is gonna, so divide by cosine to get the apparent power. So it's gonna be P over cosine theta L, where theta L here is just shorthand for theta V minus theta I at the load. Okay, so this is the formula for the apparent power. We know that, right? This is the power factor, right? So P over power factor. We know the power and we know the power factor. So this allows me to solve for the apparent power at the load. So this is going to be 25 kVA. And we said we use VA units for apparent power. Okay, but I want to get the complex power at the load. So how do I get the complex power? Well, the complex power, what's the angle? So this is the magnitude of the complex power. What's the angle? The angle is just the power factor angle, we said, right? The power factor angle is the complex power angle. Remember, complex power equals VL IL conjugate. So this is VL, this is VL IL theta V minus theta I, which is theta L, right? So the power factor angle is actually the angle of the complex power, right? So SL is just going to be the apparent power, 25 kVA, and then the power factor angle, right, kVA. What's the power factor angle, right? Well, the power factor equals cosine theta L. So the power factor angle is just going to be the cosine inverse power factor, cosine inverse PF, plus minus. Why? Because I mean, cosine is an even function, right? So theta L or minus theta L is going to give me the same power factor, right? If I bring up my calculator and do this calculation, I end up with plus minus 36.87 degrees, right? So there's a little bit of ambiguity here, but you have to remember that I didn't only give you the power factor, I told you it's a power factor lagging. That's why it's necessary to have that extra piece of information. Since it's lagging, that means the voltage, the current is behind the voltage. That means theta V minus theta I, which is theta L, should be positive. So I need to take the positive value and forget about the negative value. So SL, the complex power at the load, is going to be 25K. Let me put it down at 25,000, 36.87 degrees. All right. So now that we know SL, what's SL? SL is VL, IL, phasor conjugate. I want to use SL to calculate IL. So IL conjugate is going to be SL over VL. I want to now conjugate both sides. I want to use the basic property. If I have a complex number, conjugate it, and I then conjugate it again, what will happen? That will be equal to the same complex number, right? I have a complex number, I turn the negative component negative, multiplied by -1, and then I multiply by -1 again. That's what the second conjugation does. I end up with the original complex number. So I take the complex conjugate on both sides, I end up with IL phasor equals SL over VL phasor conjugate. So this equals 25,000, of course, and if I have F over G conjugate, that's equals F conjugate over G conjugate. You can always distribute the conjugation across multiplication, division, addition. Right? It's a very useful property to keep in mind. So the conjugation of SL is going to be minus 36.87 degrees, and VL anyway is 220, 0 degrees, so it doesn't matter. Negative of 0 is 0. Right, so if I do the number crunching here, plug it into the calculator, I end up with IL being 113.64 minus 36.87 amps RMS. Everything is in RMS right now. Okay, that's how I'm expressing everything. Okay, now remember we said, so now we have the current going into the load. Now we want to find the complex power consumed by the line. And remember we said the line is just an impedance, and we know how to calculate complex power in an impedance, right? We found out that it's just the magnitude of the RMS current, line current squared, times Z line. We did that derivation a while back, like in this lecture. Right, remember S line equals V line phasor, I line phasor. I'm just redoing it for your benefit, but you need to remember that, right? And then using Ohm's law, V line is just I conjugate, of course. V line is just I line. Did I forget the conjugate up there? No, I remember the conjugate, right? Right? So V line using Ohm's law is just I line. Sorry, is just IL times Z, right? And IL times IL conjugate gives me the magnitude, IL squared, right? That's what the number times its conjugate gives me. So this is the formula for S line. And right, and then we can calculate this. I mean, that's fine. We already calculated the magnitude of IL, 113.64 squared. What's the impedance of the line? I think I have it up there. It's 0.09 plus J.3. So it's 0.09 plus J.3. And again, take out the MATLAB or the calculator, and I end up with this number. This complex number, VA. Okay. Now, we said from the conservation of power, I mean the amount. So in the circuit, the amount of complex power consumed by the line and the load is going to be equal to the amount of complex power sourced or supplied by the source. Right, and the total amount of complex power consumed is just going to be the sum of those two complex powers. So the total complex power. So this is the total complex power consumed by the circuit, which is equal to the total complex power supplied by the source. It's just going to be SL plus S line. Right, so that will give me the total complex power consumed by the circuit. So that will be 25,000. 36.87, we already calculated that, plus 1162.26 plus J 3874.21, and this, just turn this into rectangular and sum it up. I end up with 2116.23 plus J 18874.27 VA. Turn that back into polar coordinates. I end up with 28356.27, 41.73 degrees VA. Okay. And now I'm in a position at calculating the voltage at the source, right? So I know that Vs just equals the apparent power over IL, right? I know this now. I know the magnitude is 28356.27. And I know what the magnitude of IL is. I calculated it previously. It's 113.64. So I calculated the magnitude of the voltage at the source without using KVL, just using the power concepts, to be 249.53 volt RMS. What about the power factor at generator? So we said that the complex power angle is the power factor angle. It's the same, right? From the formula. Turns out to be the same thing. So the power factor at generator, let's call it PFS, is just cosine the power factor angle, 41.73. This turns out to be 0.75. And because this is a positive angle, that means the voltage is leading the current by 41 degrees, meaning the current is lagging the voltage by 41.73 degrees. So we say this is 0.75 lagging. Remember, it's when you're specifying power factor, it's not enough to state the number representing the power factor. You have to state whether the power factor is leading or lagging. All right, guys. Thank you. See you next time.